This is a tutorial for how to use command-based in C++. So first we're going to create a new command-based project by going to File, New, Other, making a robot C++ project, selecting command-based, and making a new project. So we're going to go over how command-based works and create a very simple robot using command-based. So command-based is an extension of iterative robot that adds the structure of commands and subsystems to control your robot. So the way you structure command-based programs is you split the components of your robot into subsystems. So for example, the motors and the encoders from the drivetrain might go into a drivetrain subsystem, while, say, a shooter motor and maybe a switch for the shooter might go into a shooter subsystem, and so on. And then commands are classes that take action on certain subsystems. So you might have a fire command that takes action on the shooter subsystem to perform a certain set of actions. And then those are bound to joystick controls in the operator interface, which is where the human interface controls are defined. And similarly, like autonomous routines are defined through commands and then bound to the autonomous routines in question. So we're going to start setting up our basic robot here. So the first thing we're going to do is get rid of these example subsystems and commands they've given us, because while they're useful as empty files, they're not very nicely named. And if you get all these errors like I have, just go ahead and refresh your index, and it should all clean up. I might have to rebuild the index, actually. But once that's finished indexing, it should all go away. I'll let that finish up. So we're going to create, for this project, a new subsystem and a few new commands. So we're going to be putting everything into one subsystem, the drivetrain subsystem. But realistically, in a real competition robot, you'd probably have multiple subsystems for each portion of your robot. So this drivetrain is going to contain a few things. We're going to have to include some headers here. We're going to be using the robot drive class. We're going to be using the encoder class. We're going to be using the digital output class for an LED. So we're going to have some members here. So we want pointers to these so that, because they're going to be used really all over, we want them to be able to be passed around. All of these classes also have their copy constructor and copy assignment operators deleted. So it would be difficult to construct them after they've been default constructed if we stack allocated them, or rather allocated them inline. So we're going to use pointers. And of course we're going to use unique pointers, because we never use owning raw pointers. So we're going to have a left encoder and a right encoder. And we're going to have a digital output. And I just realized I forgot the FRC namespace. Okay, so we have all the components of the subsystem now, Now we have to add some functionality through these public methods. So this is the basic interface for a subsystem, is its constructor, obviously, and a function that sets a default command that should run by default when the subsystem is initialized. You don't have to have one. For something like a drivetrain, it's very useful for, say, the drive command or such to be the default. So this is going to have two different interface functions that we're going to declare now. We'll define them later. It'll have one to tank drive with left and right speed parameters. And it will have one to arcade drive. And the reason we have to do this is we've made the member objects private, so we have to provide a way for the commands to interface with the drivetrain, and we're going to do that through these functions. So these internally are going to call member functions for these objects, but we'll write them in a bit. So next thing that we have to do now that we've set up this subsystem is to go to command base, where we register all of our subsystems and essentially replace this example subsystem that they had as a placeholder with our new subsystem. So we're going to change these all to drivetrain. And what command base essentially does is keep a single instance of all of your subsystems, a static instance of each of them around, for all the commands to be able to access and use. Okay, so that should be all for a command base. And now we're going to go make a new command that utilizes the subsystem. So we're going to go and make a new command. And we're going to call this one joystick tank drive. So this is going to be tank drive using a joystick. So you'll see commands all have this common interface and their constructor and these 5 functions. And as the comments here will explain, initialize is run just before the command runs the first time. Execute is what's called during the command's execution in a loop. Is finished, we'll check if the command is finished. End will be called when the command ends, and interrupted will be called if the command is interrupted by another command, so it can do any cleanup that it has to. So in the constructor for joystick tank drive, we're going to declare any subsystem dependencies that it has. So in this case, joystick tank drive relies on access to the drivetrain subsystem. So we're going to do requires command base drivetrain.get. So this declares that this subsystem requires access to that. This command requires access to that subsystem. If any other command is using it when this is called, it will interrupt it. And similarly, if this is using it and another command requests it, this could be interrupted. So it's important to declare these dependencies so you don't have conflicting commands running. And without this information, the scheduler has no way of knowing if they could conflict. So to initialize, there's really nothing we have to do here. For more complex commands, you might have some setup, some pre-calculation or something. The next thing we do is we write the code that executes in this. So all it does is it calls the tank drive function, and what does it pass in for the left and right parameters? Well, it's going to come from the joysticks, but we haven't declared the joysticks yet, so we'll come right back to this. We'll go into the OI, the operator interface, and we're going to declare those joysticks. So we're going to make a again, a unique pointer to a joystick, and we have to include this. And then in the constructor for the operator interface, we're going to construct a joystick on port 0. So now we have our joystick. So here we can say the command base also keeps track of a copy of an OI object. In fact, the only OI object that should be in your program. So we can use that, and we can say we want to get, let's say, we want to get axis 0 and axis, let's say axis 2, for example. So the actual axis port numbers that you want will be dependent on your hardware. So these are just made up numbers for the sake of demonstration. And we are essentially never finished, right? Like this command will never finish on its own. We always want to be able to drive. And when we're done, we want to stop the motors. So we're gonna copy this, but we're just gonna set this to 0. Cool. So this is our tank drive command fully written. So the next thing we can do is actually set it up as the default command for our drivetrain subsystem. This is what we want it to do by default. So set default command new and we will have to include this file, but once we've done that, our drivetrain subsystem is complete. So now we just have to go back to the robot.cpp, and in fact, you don't even have to change anything here, because if you see, and if you don't know about how iterative robot works, go ahead and watch the iterative robot tutorial. But in our Telia periodic, we just run the scheduler, which will automatically look at the drivetrain subsystem and run its default command, which is the joystick tank drive. So in terms of basic driving around, we're all set. But let's get things a little bit more interesting. Let's add a button on the joystick that, when held, will put us in arcade drive mode. So first thing we're going to want to do is create a new command for arcade drive. So this is going to be for a command-based sample. And this is going to be super similar to our tank drive code, so much so that we can probably just copy-paste a lot of this. So it's going to require the exact same subsystem, which is important. This way they won't conflict with each other. It's going to do roughly the same thing and execute. And it's going to do the exact same thing once it ends. The only difference is that it's going to run the arcade drive function now. And this time we'll say that we're using axes 0 and 1. So this is why we set up both functions originally inside of our subsystem. Now with just a few quick tweaks we can set up an arcade drive command in no time. Now the question still remains, how do we get this thing to run when we hit a button? So all of the human interface stuff is handled in OI, so that's where we're going to go. So what we're going to do is we're going to essentially set up a new button and bind it to that. So here we're going to say and we're going to So we're actually going to declare a joystick button. And we're going to call it button arcade. And we're going to do this in buttons, joystick button.h. Okay, so we actually had to include buttons / joystick button.h, and we have a joystick button that we're going to call button arcade. And then in our oi.cpp, what we're going to do is okay, so what we're going to do is we're going to set up this button. So button arcade equals we're going to pass in the joystick that it's going to be referring to, as well as the button number on the joystick, and we're just going to arbitrarily say it's button 0. Again, on your own joystick, you'll have to confirm these numbers through testing. And we're finally going to bind it to a command. So we're going to say button arcade dot while held, and we're going to make that bind to a new joystick arcade drive. So now we just have to include the correct header. Okay, so now this business of including these headers here is kind of messy, but this is a quick and dirty project, so we'll go with it. So now we have a new button that, while held, will trigger arcade drive, and only while it's held. As soon as it's released, the default command will kick back in, you'll go back to tank drive. So this is pretty good. We've got a pretty good thing going here. The last thing we're going to do is set up an autonomous command. So we're going to make one last command, and we're going to call it our autonomous command. And this command is going to also require that drivetrain. And what this is going to do is it's going to essentially turn on that light. So all it's going to do in execute is say so we don't actually have an interface function for activating this light, so we'll have to create that actually. So we'll say void set light, and all this function will do is okay, so now that we have that, we can fill this in. We can set the light to true, and then once we're done, we can turn it off. So this is a really simple autonomous command, but I'm going to show you how you bind it to the autonomous. So you would come in here to robot.cpp, and you would here this autonomous chooser. So you would you would include this command. So you would include autonomous command, and then you would comment this line out. Default auto will be the autonomous command, and that will send that and any other autonomous commands you add this way to the chooser on your smart dashboard. And again, watch the iterative robot video to find out exactly how that would work, but it's a simple process. You just include your autonomous commands and add them to your options list. So this is pretty close to being done, but we've got a few loose ends left to tie up. For one, we never actually initialized these objects we've got here, these drive, this encoder, and this digital output. And we've got to do that in this constructor here. So we're going to use one last file called robot map to specify all the ports we need for this. So if we go into robotmap.h, we see that it's a place for specifying constants, essentially, ports that we're going to have to use. So here, I don't have an actual robot, so I'm going to make up some ports, but you would, of course, go find the actual ports on your robot for this. So I'll say the left motor is plugged into 0, right motor into 1, the left encoder. As I mentioned in the iterative video, the encoders tend to have two ports they use, so the A port of the left encoder will say 0, the B is in 1, and so on. We'll say the light is in port 0 and the joystick is in port 0. Okay. And also, as I mentioned in the iterative video, we're going to need a value for so now we can go back to our drivetrain and initialize these values. So we can say let's make unique of a robot drive with the parameters L motor and R motor. Similarly, this should be right encoder. My mistake. So we're going to say left encoder equals and right is going to be very similar. and then finally the light. So those are all of our drivetrain things. And finally, in our OI, I guess we don't really want to hard code this, so we can use the robot map and instead say joy. And I believe we have to include that. So now we've factored out all our constants into a separate file. So there's really not much else left to do. Now I haven't showed off all the possible functionality of command base. It's a really rich set of functionality that you can spend a lot of time learning. For example, in OI, there are several different button modes. You can do things when a button is held, when it's pressed, when it's released. You can create things called command groups, which let you chain together series of commands as a new command. You can do lots of complicated things within commands, use multiple subsystems and synchronize between them. So command-based is a really, really powerful way to manipulate your robot that's simple to learn. So that's command-based.